welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless communications. All right. So, in this module, we have started looking at developing a framework to characterize the reliability of the MMSE estimate. All right, and this can be characterized as basically finding the number of samples such that with probability greater than 0.9999. The difference between the estimate h hat and the true parameter h should be less than or equal to sigma over 2, all right. And we have said that this mean square estimation error, that is, if you look at this mean square estimate, if you look at this estimation error, that is W, it is Gaussian with mean 0 and variance sigma tilde square. Therefore, its probability density function is 1 over 2 square root of 2 pi sigma tilde square e raised to minus w square by 2 sigma tilde square. Okay. And we need to find, we need to have the condition probability magnitude w greater than or equal to sigma by 2 must be less than or equal to, well, this must be less than or equal to 10 to the power of 4. This is what we have already seen. Now, the probability magnitude w greater than or equal to sigma by 2, this implies either w is greater than or equal to sigma by 2 or w is less than or equal to minus sigma by 2. Okay. And the probability, sum of the probabilities corresponding to both these scenarios must be less than or equal to 10 to the power of minus 4. Okay. Now, if you can see, basically this w is a Gaussian random variable. So, its probability density function is symmetric about 0. Therefore, the probability that w is greater than or equal to sigma by 2 is the same as the probability that w is less than or equal to minus sigma by 2. Okay. Now, probability this, now therefore, we have, since PDF of w is symmetric, about 0. Okay. Therefore, the probability that w is greater than or equal to sigma by 2 equals the probability that w is less than or equal to minus sigma by 2, and therefore, the probability this, basically you can simplify it using this property, that twice the probability w is greater than or equal to sigma by 2 has to be less than or equal to 10 to the power minus 4. Taking this factor of 2 to the other side, this implies that the probability w is greater than or equal to sigma by 2 has to be less than or equal to half into 10 to the power of minus 4 equals 5 into 10 to the power of minus 5. Now, what I am going to do is, I am going to do something interesting. I am going to divide this by probability of w divided by, if w is greater than sigma by 2, w divided by sigma tilde is greater than or equal to sigma by 2 divided by sigma tilde, which is equal to 5 into 10 to the power of minus 5. Okay. Now, observe this quantity, w is a Gaussian random variable with mean 0 and variance sigma tilde square. Therefore, w divided by sigma tilde is a Gaussian random variable with mean 0 and variance 1. Okay. And this is the principles that we are going to. W is Gaussian random variable with mean 0, variance sigma tilde square, implies w divided by sigma tilde is Gaussian random variable with mean 0 and variance 1. This is also known as a standard Gaussian random variable. This is also known as a standard Gaussian random variable, because mean equals 0, variance equals 1. Okay. For any Gaussian random variable x, if x has mean mu, variance sigma square, then x minus mu divided by sigma is also Gaussian, and this has mean 0, variance 1, that is a standard Gaussian random variable. So, W already has a mean of 0. So, W divided by sigma tilde has mean 0 and variance 1. Okay. And now we have what is the probability. So, we have implies the probability W divided by sigma tilde greater than equal to sigma by 2 divided by sigma tilde, that has to be less than or equal to 5 into 10 to the power of minus 5. And this function, this quantity, the probability that the unit norm, the standard Gaussian random variable with mean 0 unit norm is greater than or equal to any quantity x is given by q of x. So, this implies this q of sigma by 2 divided by sigma tilde is less than or equal to 5 into 10 to the power of minus 5, where what is the q function? Let me define the q function. Q of x equals the probability that x greater than or equal to this quantity x, where x is the standard Gaussian random variable, that is x is a standard Gaussian random variable, mean 0, variance 1. So, we are saying the probability that W divided by sigma tilde, which is a standard Gaussian random variable, is greater than or equal to sigma by 2 divided by sigma tilde, that is q of sigma by 2 divided by sigma tilde. Therefore, we need this quantity q of sigma by 2 divided by sigma tilde. This quantity has to be less than or equal to 5 into 10 to the power of minus 5, which implies sigma by 2 divided by sigma tilde. This has to be greater than or equal to twice into q inverse of 5 into 10 power minus 5. You can see inequality is reversed, the lesser than becomes a greater than, because q function is a decreasing function. Inequality is reversed, inequality is reversed because q of x is a this is a decreasing function. Therefore, q of x is less than or equal to t implies x must be greater than or equal to q inverse of t. That is the principle that we have used, because the q of x is a decreasing function. That is why when you take the q inverse to the other side, the inequality gets reversed. Okay. So, basically that implies now that implies, sorry, this 2 will not be here because we are taking this 2 to the other side. Now, let us substitute this expression for sigma tilde. Sigma tilde is the square root of the variance, that is the standard deviation of the estimation. Remember sigma tilde square, remember where we got this sigma tilde square is variance of W, and sigma tilde square equals 1 over sigma square by n plus 1 over sigma h square. So, this implies what does this imply? Basically, this implies your sigma divided by sigma tilde, which is square root. So, sigma tilde square equals this, which means sigma naturally equals to square root of this 1 over square root of 1 over sigma square by n plus 1 over sigma h square. This has to be well greater than or equal to twice q inverse of 5 into 10 to the power of minus 5. This implies that sigma times square root of 1 over sigma square by n plus 1 over sigma h square should be greater than or equal to twice q inverse 5 into 10 to the power of minus 5. Now, take the sigma inside. This implies square root of, well, you take the sigma inside, what you have is n sigma square divided by sigma square divided by n, that is n plus sigma square n plus sigma square divided by sigma h square must be greater than or equal to 2 twice q inverse 5 into 10 power minus 5. This implies n plus sigma square divided by sigma h square greater than or equal to twice into q inverse 5 into 10 power minus 5 whole square. You can evaluate this using the using either a computer or using the q function tables. You can evaluate this. So, this let us say you evaluate this, all right, I am leaving this, you can evaluate this, evaluate using the, for instance, you can use MATLAB or q function tables, etc. Okay. So, you can either use MATLAB or a q function table, that is printed values of the q function for various values of the argument. Okay. You can use it to evaluate this constant, and that will be 60.54. Okay. And therefore, what you have is n must be greater than or equal to 60.54 minus sigma square divided by sigma h square. Okay, sigma square divided by sigma h square. And what is sigma square? Sigma square equals, let us remind you once again, sigma square equals variance of noise, and sigma h square, this is the prior variance of the parameter. Sigma square divided by sigma h square, and this is the prior variance of the parameter. And now we have derived our number of samples that is required. And remember, let me explain to you, this number of samples that is required is basically the number of samples that is required. If you go all the way back and you recall what we were deriving, this is basically the number of samples n that is required such that the probability h hat lies within sigma by 2, that is it lies between, that is h lies between h hat minus sigma by 2 to h hat plus sigma by 2, that is h lies within the sigma by 2 ball of the true parameter h. The probability with which it lies in the sigma by 2 ball around h has to be greater than or equal to 0.9999 or with 99.99% reliability. Okay. That is how we had derived, and now we have derived that this number of samples n that is required for this purpose is n equals n is equal to 60.54 minus sigma square divided by sigma h square. Okay. Let us look at a simple example to understand this. Again, let us go back to our WSN. Let us go back to our wireless sensor network example. Remember, we had the dB variance dB noise variance equals minus 3 dB, right, implies 10 log 10 sigma square equals minus 3 implies sigma square equals 10 to the power of minus 0.3, that is equal to half. We also have the prior variance sigma square h square equal to 1 by 4, this is the prior variance. Therefore, we derive that n is greater than or equal to 60.54 minus sigma square by sigma h square as we have derived above, that is basically your 60.54 minus half divided by sigma h square, which is 1 by 4, which is basically half divided by 1 by 4 is 2. So, this is 60.54 minus 2, that is 59 point, that is basically your 58.54, which implies that n has to be approximately, n has to be greater than or equal to, implies n has to be, since we have an integer number of samples, n has to be greater than or equal to 59 samples basically. That is what we have derived. N has to be greater than or equal to 59. We need n greater than, so need n greater than equal to 50. So, let me summarize this again. We need n greater than or equal to 59, so that probability magnitude h hat minus h, so that the probability h hat minus h greater than or equal to sigma by 2, this is less than or equal to basically 0.9999, which means it lies inside this sigma by 2 ball with probability greater than or equal to 1 minus 0.9999, that is as we saw 10 to the power of minus 4. Okay. So, now we have a neat framework, an elegant framework to basically characterize the reliability of the estimate, alright. And we have seen as the number of samples n increases, the variance of the estimate, the MSE, mean squared error of the estimate, decreases, which is also the same, the mean squared error in this case is also same as the variance of the posterior density of the parameter h, which means as the variance is decreasing, remember the mean is h hat, alright, the variance is the spread around the mean h hat, which means as the variance is decreasing, the spread around this mean h hat is decreasing, which means in probability, like probabilistically speaking, the true parameter h is closer and closer to h, that is with a very high probability, with a very high degree of certainty, the true parameter h is very close to the estimate h hat. Now, to characterize that precisely, how many samples n that are required to achieve a certain degree of certainty or a certain degree of reliability, that is what we have derived in this module so far, and we have shown that for our simple wireless sensor network example, we have shown that if we require such reliability, then we need n greater than or equal to 59 samples, alright. And you can carry out this analysis for other examples with other values of sigma s square, sigma h square, and also more importantly with other desired reliability criterion. For instance, we have assumed a reliability criterion of 99.99%, you can make it 99% or 99.9999% and so on, and you can explore how this answer varies with this varying degrees of reliability, alright. So, basically this is a framework which shows you how to choose the number of samples for the MMSE estimate, number of samples in the MMSE estimation process, so as to achieve a desired degree of accuracy and reliability, alright. So, we will stop this module here and continue with other aspects in the subsequent modules. Thank you.